Hello everyone, my name is Fengcai Wen and I am a PhD candidate from Software Institute at Università della Svizzera Italiana. Today I'm going to introduce you our two demo paper that presents a recommender system that can suggest the next method to be implemented for Android applications. The initial work on building this recommender system had been published in ICSME 2021. However, in this two demo paper, we focus on the engineering part of building FeaRS, and we also release FeaRS as an open source project. Let me first show you a concrete example of our motivation. Here is a typical tutorial related to Android development. It shows how to find and display the location details of an Android device. First, the tutorial shows a sequence of methods need to be implemented to check and request the location permission. After handling the permission, developers should implement another group of methods to display the map information on the Android device. From this example, we can consider the sequence of methods implemented for specific tasks as a code implementation pattern. If we can identify and collect those patterns that are commonly used by developers, then we might be able to predict the next method in a given context. Next, let me introduce you the architecture of FeaRS, which is composed of three major components: the offline analysis, a web service, and an IDE plugin which can be installed in Android Studio or IntelliJ IDEA. First, let me briefly discuss about the offline analysis, which consists of two subsystems. The first one is FeaRS Crawler, which retrieves and clones thousands of Android apps using the GitHub API. And the second one is FeaRS Analyzer. It performs 3 steps of data processing to learn the implementation patterns. Each pattern is presented with the left-hand side and the right-hand side, which indicates that whenever a developer implemented the methods on the left-hand side, very likely he is going to implement the right-hand side method as well. And importantly, each method here in the pattern is a representative of all similar methods from the repository. You can find the detailed approach behind this analysis in our paper. In addition, this offline analysis automatically checks for project updates, including new commits from old projects and new projects since the last round of crawling. The knowledge base is then updated every 3 months in order to continuously improve the recommendation capabilities of FeaRS. After the offline analysis is finished, the web service is ready to host the knowledge base and process the request from the user side. Now we can take a look on the actual workflow of using FeaRS as a developer. After the plugin is installed in the Android Studio or IntelliJ IDEA, the developer can press the button to start monitoring the code changes from the IDE. After a new method is implemented by the developer, this method will be sent to the web service in a JSON format to check if it can be matched to an existing representative method in the database. If the answer is no, then no recommendation will be generated. If yes, then we check if there is any implementation pattern having this method as the left-hand side. If no, again, nothing to recommend. If yes, the web service will recommend this method from the right-hand side of the matching patterns. Now the plugin interface would display all the possible recommendations received from the service. And then the developer can start copying the code snippets from the plugin. In addition, a command documenting the GitHub repository from which the snippet has been taken is added to the code as well, so the developer can check its reusability from a legal perspective. Finally, I would like to shortly describe the evaluation part. We evaluated the performance of FeaRS using the historical data in open source repository. We first retrieved and cloned 21,000 Android applications. Then we collected all the commits from the complete history of each application, and we divided the dataset into two sections, namely the training and the evaluation set. For the training set, we run the offline analysis to learn the implementation patterns. Then we check if those patterns can be applied to make good recommendations on the evaluation set. There are some cases that FeaRS is able to make good recommendations, some cases bad recommendations, and some other cases no recommendation at all. The precision would be the number of good recommendations divided by the number of generated recommendations, and the recall would be the number of good recommendations divided by the number of all instances in the evaluation set. The final precision value shows that when a recommendation has been generated by FeaRS, it is very likely to be applied by the developer. And the recall value may look low, but considering the size of the evaluation set, we can still make good recommendations for over 3,000 commits. Also, we hope the performance can be improved overall with the continuously running offline analysis. To conclude this presentation, we first showed the idea behind building FeaRS, and then we introduced you the architecture of FeaRS. Then we presented how FeaRS works from a user's perspective. At the end, we briefly discussed about the preliminary evaluation result of FeaRS. If you are interested in our tool, please feel free to check the links below, and thank you very much for watching.